Hey guys, so what I'm going to be doing today is I'm going to be going over the review for the test that we are taking on Thursday, which is our midterm, and it's going to be over Earth's layers and plate tectonics or continental drift. So to start off with, we have the layers of Earth. We've got the inner core that's at the very center, which is number 6 here. And then outside of that, if you look at the diagram that I stuck in here at the bottom, we have the outer core. And so that's going to be molten iron and nickel. The inner core is going to mostly be iron, while the outer core also contains nickel. And then I have the mantle, which is the thickest layer, and then the crust. So this picture is obviously not to scale, but I'm going to have the mantle be the thickest layer here. I wanted to mention the lithosphere and the asthenosphere. So I'm going to draw a picture here at the bottom. If I have the inner core and the outer core, and then I have the mantle, which is very thick, and then I have the crust, which is very, 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 very thin here. This is the lithosphere, okay? That's supposed to be an L right there. I'm trying to make it darker. So that's my lithosphere, which is basically the crust and the part of the mantle, the top part of the mantle that the crust is touching. That's my lithosphere. And then my asthenosphere is underneath that. It's basically where the convection currents are happening, right? So here I've got my convection currents. So that's the asthenosphere right there. And the way that I remember this is I think Los Angeles, LA. And so the L is on top, lithosphere is on top, and then the asthenosphere is underneath that. Okay, so that's a trick to help you remember the difference between the lithosphere and the asthenosphere. Then I've got a few questions here. What elements make up the majority of Earth's layers? It's going to be iron and nickel. Those are the main ones, but you're also going to have magnesium, oxygen, and silicon. How do we study the Earth's interior? And I included the same picture again here to show how we use seismic waves, which are able to travel through Earth. So how do we know that Earth is made of all of these layers? We've never been down there, right? We've never dug deep enough to see the mantle, let alone the outer and the inner core or anything like that. We've only been able to go through a little bit of the crust. And the way that we know what is in there is because of seismic waves. Let's say that there is an earthquake on one side of Earth. We have seismographs all over Earth measuring vibrations and measuring earthquakes. So even if there's an earthquake way over here, okay, and Eagle Pass is over here on the bottom right, let's say we have a seismograph here, they can use that seismograph to measure vibrations from the earthquake that was on the other side of Earth. And what they noticed when they did that is as the vibrations were traveling through Earth, they eventually get to the other seismograph, which is way over here, and the waves were changing speed. When we're talking about vibrations, which is mechanical energy, it's going to go faster through things that are more solid and slower through things that are liquid or gas. And so Earth is made up of layers, right? And those layers are going to either be kind of liquidy or kind of solid-y, right? Or super solid. And so what they noticed is that it would go kind of slow. So I'm going to draw in a different color here. It would go kind of slow and then faster, 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 and then slow down, slow down, slow down, as it was going through Earth. And they were kind of like, how come it's changing speed as it's traveling through the Earth? Oh, well, it's because it's made of different materials, and some materials are solid, and some layers are liquid, and some are solid. And so that's how they were able to figure that out. Another way that we know specifically what the mantle is made of is volcanoes. So I'm going to draw a volcano over here on the side. So we know that magma will erupt from the volcano, and what typically happens is this stuff will turn into rock, which is basalt, and basically looks like a black rock, but sometimes there's green rock that comes up, which is called the gemstone's called peridot, or it's also called peridotite, and it's got this mineral in it called olivine, and that comes from way down deep. And we know that, hey, that's kind of weird stuff. You know, where did that come from? Well, we know it came from down deeper, meaning the mantle. Okay, so we know that sometimes these chunks of green stuff erupt from volcanoes, and we know, hey, that's not just regular magma or lava that always erupts from volcanoes. It's something that's coming from way down deeper. It contains different stuff, and that's actually mantle rock. Okay. Number 9, explain the relationship between temperature and pressure as you go deeper into the earth. The deeper you go, right, the temperature is increasing and the pressure is increasing, because all of these layers here are pushing down, and so the pressure is increasing as I go down deeper. Next one, we've got solid, S for solid, S for semi-solid, meaning kind of liquidy or totally liquid, is L, and then it compares it to an egg, right? The shell of the egg would be the crust, and then underneath that, the thickest layer is the egg white, that's the mantle, and then the egg yolk is the core, which is split up into the inner and the outer core. This was a little bit confusing, but the next page actually explains a little bit better, I think. So, the greatest is 1, like meaning if it's very thick, it's a 1. If it's not thick, then it's a 4. Or if it's got a high temperature, it's a 1. If it's not a very high temperature, it's a 4. If it's something that's very dense, it's a 1. If it's not very dense, it's a 4. So you can see the breakdown that you've got right here for that. But let me go on to the next page, because I like the way that they set this up a little bit better on the next section. So here they compare the inner core and the outer core, and tell you like what the difference is here. So the inner core is mostly iron, while the outer core is going to be iron and nickel. The inner core is going to be very dense, right? Because remember all of that pressure that's pushing down on it. The outer core is a little bit less dense. We have a lot of pressure in the inner core, and then a less pressure on the outer core. And then the inner core is smaller, thinner, and the outer core is thicker. And the inner core is solid, mostly because all of that pressure that's pushing on the inner core is making it a solid. And then the outer core is a little bit more liquidy. So both of them are layers of Earth. They have high temperatures, which is because of the pressure, and they're located between the crust and the mantle, and they both contain iron. Here's that picture again where we've got the inner core, outer core, mantle, and crust. Tectonic plates. These are just straight up from your notes. You need to memorize them. You need to know, where's what. There's more plates than this. The smaller plates, like the Caribbean plate and stuff like that, they're not labeled here. So those are kind of like the subplates, but these are the major ones, and you need to know them. You also need to know where we live, right? So 5, which is letter D, is the North American plate. That's where we live. And some of these are pretty common sense, right? Like number 6, you should already know, oh, that's the African plate, okay? Number 1 is another really important one, because that one affects us a lot where we live. That's the Pacific plate, okay? Number 2 should be pretty straightforward too, the South American plate. So just make sure that you study these and that you know these, and make sure that you know where we are, right? We are here on the North American plate, and Eagle Pass is like right there, if you can see the little dot that I just drew. Name 3 other tectonic plates that are not listed above. So these would be the subplates, right? So we've got the Somali, Caribbean, Philippine, Arabian, Cocos, Scotia, and the Juan de Fuca plate are just some of them. How are scientists able to determine that there are different plates on Earth's surface? When this we know because of geologic events. So when they're crashing into each other, the convergent boundaries, divergent, and transform boundaries that cause all these things like earthquakes, volcanoes, mountains, all of those things are happening, so we know that the plates are moving. How is it possible for tectonic plates to carry continent, ocean, or both? And it's all because of the convection currents that are pushing those plates on top of it. The example that I like to use is like a floaty. You know, those floaties that you can lay down on in a swimming pool. If you were to take the floaty and put it in a river, it's going to move in the same direction that the water is flowing, right? And that's what's happening with these plates, with this lithosphere that's broken into sections on top of the magma. The magma is moving in a certain direction, and the plate is going to move in that direction too. And depending on if there's two plates next to each other crashing, it's going to cause different things than if they're dividing and things like that underneath them. Okay, if the convection current is making them divide. Here we have another Venn diagram to compare and contrast tectonic plates and continents. So here we've got major tectonic plates or continents, and then we have some secondary or subplates. Tectonic plates are going to consist of continental or oceanic crust. In other words, if there's land, or if it's ocean on top of that, and they're going to be crashing into each other with, you know, to make those divergent, convergent boundaries. They both have different shapes, they're different sizes, they're solid, and they can have fractures or breaks in them. And then for the last one here, for continents, most continents do not share borders or boundaries with other continents, with other major continents. Matching. Geologists are scientists, right, that study rocks and plate tectonics and all of that stuff. Geo means earth, and then ologist is somebody who studies science. Number 14, a tectonic plate is a broken section of the lithosphere that's moves, right, and it's carrying continental or oceanic crust on it. And then number 15 is a fault. So that's a break or a crack in Earth's lithosphere. So that's where we're going to see movement. Number 16 is one of the plates that's actually right by us. This plate, the Juan de Fuca plate, is actually what causes Mount St. Helens to erupt. Number 17 is the Scotia plate. That's another plate between South America and Antarctica. We've got number 18 is the Caribbean plate between North and South America. Number 19, remember lithosphere and asthenosphere. So the lithosphere is the uppermost section. This is the crust right here, crust. And then convection currents are those currents because of density, right? We have magma that's heated and moves away from the core and floats up and then gets cool and sinks back down. And it's all because of density. Stuff that is hot is going to rise, and stuff that is cool is going to sink. We have three types of plate boundaries: convergent, collide, they crash into each other; divergent, divide or separate from each other; and then transform, plate boundaries slide past each other, and that's what's going to cause earthquakes. So here on the left hand side you have the type of plate boundary, and it's telling you if it's continent or oceanic. So this is the pink paper that we glued into your notes. If it's continent to continent, convergent, that means two land masses are crashing. I'm going to create the Himalayan mountains. Okay. If I have continent to ocean, convergent, in other words, land and ocean are colliding, that's going to create something like the Andes Mountains or volcanic mountains. This one is going to be a subduction zone, okay, because the oceanic, so I'm going to write here, subduction, because the oceanic is going to subduct under the continental plate. Then if I have ocean to ocean convergent, this is going to cause volcanic islands like the Aleutian Islands, which are in Alaska. And so two oceanic plates are going to collide, and then it makes a chain of volcanoes where they crash into each other. Then I have continent to continent divergent. That means two pieces of land are dividing, and this is happening in Africa, in the Rift Valley. Okay, then I have ocean to ocean divergent. This is in the middle of the ocean, and they're dividing from each other, and this is the mid-ocean ridge or the mid-Atlantic ridge. So where the oceans are growing. This is happening in the Atlantic Ocean, right? The United States and Europe are getting further and further away from each other. Then we have transform, which we're going to have them sliding past each other, which causes earthquakes like the San Andreas Fault. Remember that plates move very slowly. They move at about the same rate that your fingernails grow. What is a plate boundary? It's going to be when two plates are coming into contact with each other, they're interacting with each other. We have two types of crust: continental, meaning land, Okay, I'm going to write land right here. And we have oceanic, which is ocean. And oceanic crust is more dense. So then that means like if I have oceanic crust right here, it's going to get subducted over continental crust. What two types of rock make up a large majority of the composition of Earth? Granite, which some of you guys might have in your kitchen, which is an igneous rock, and then basalt is also igneous. That's oceanic crust. It's a black looking rock. Briefly describe the process of subduction, right? Subduction, like submarine, one goes underneath the other. So it sinks underneath the other because it is more dense. What is a deep ocean trench? This is where one plate subducts under the other. So right here, if I look at my number 5 again, this is my trench right there. Then describe the process of seafloor spreading is when I have like the mid-Atlantic ridge. The plates are separating from each other, and the new magma comes up in between and creates new land as they spread apart. The Hawaiian Islands, how are they formed? I'm going to draw a picture, so prepare yourselves. With the Hawaiian Islands, I'm going to have a hot spot where I have magma that comes up in the ocean. So let me draw some water. Okay, this is my water. And so the magma comes up. Oops, let me change back to red. The magma comes up and it creates a volcano here. And then the land is moving along. It's moving this way. Okay. And then the new land underneath is on top of the hotspot, and so then I start creating a whole chain of islands right here. So here's like a newer island, and then a newer island, and that's what makes a chain of islands in Hawaii. So as the plate's moving, the hotspot is erupting and making more and more islands. And once the island, like the first island here, is not over the hotspot anymore, then it can't grow anymore. So basically the island is not gonna continue. There's no more land that's going to be made there. The newest land that's going to be made is going to be only the part that's over the hot spot. We have another Venn diagram for convergent and divergent. So remember, convergent, collide, divergent, divide. Okay, so they're either crashing into each other, coming towards each other, or dividing, spraying apart from each other. Convergent, we're going to make mountains, or even volcanic islands, like I just said, with the Aleutian Islands in Alaska. And then divergent, we're making rift valleys or mid-ocean ridges. They're both plate boundaries. They occur at different locations on Earth, and they both can cause earthquakes. You're going to get earthquakes in all of these locations because there's movement. And last but not least, we've got a really great diagram that I really like here that you should label. So divergent here, they're separating from each other. Down here, you've got magma. Okay, here you've got subduction because one is going underneath the other. And then this continental crust is coming this way. It's kind of missing an arrow right here, but that's why it's considered a convergent boundary, because these two plates are crashing into each other. And here we've got oceanic crust, because technically this should be blue if you want to color it blue. This is all ocean right here. And then this is continental crust over here. So this is all continental crust. So that's land right here, and it's making a volcano. So what happens here is that this subduction zone, as it's going down this way, it's going to erupt and then make the volcano erupt right here. So it's causing a volcano there at that subduction zone. And then over here where we have our divergent, new magma will come up here and fill in the spot and make new land or new crust underneath the ocean. So that's our mid-ocean ridge. Okay, so study for your test. Thank you for watching this video. I'm very proud of you for studying, and I will see you in class. Let me know if you have any questions. Thanks.